Hey everyone, welcome again to one of our live sessions, live Q&A and discussion session here of World Science U, World Science Festival, your daily equation, whatever you want to call it, a hybrid of all of the above. And as advertised, I think some of you saw that we're going to have a conversation about dark matter in, second part of the live Q&A today, where we're going to talk about some wonderful new research that has been spearheaded by a friend of mine and colleague from Yale, Priya Natarajan. And we'll be bringing her in and having a conversation about some ideas that at least have the potential to upend our understanding about dark matter. And that's really exciting. I mean, dark matter, as we'll discuss in that conversation coming up, has been around as an idea for nearly 100 years. Well, actually, references to dark matter, it turns out, go even further back than 100 years, as it turns out, as we may discuss. But still, we don't know what the dark matter is. And in fact, we're not even completely sure that the dark matter exists. So that'll be part of our upcoming conversation. Begin with a little bit of news. You may have heard this exciting and curious result that may hint at the existence of life on Venus, the discovery of phosphine in the atmosphere of Venus. Now, look, when we think about life in the solar system, the dominant place that we've long turned as a potential habitat for life beyond Earth is Mars, right? I mean, you see that in so many science fiction episodes. Obviously, we've sent rovers to Mars in search of evidence of life. Venus has always been looked at as a much more forbidding place. I mean, there's a good reason for that, right? I mean, the temperature is extremely hot. It's so close to the sun. It's got this atmosphere that holds in the heat, over 800 degrees, I think, very high pressure. But some scientists are at least suggesting, and I don't think anybody's going out on a limb and saying that this is proof of the existence of life. Maybe people are saying that. I haven't really heard that. But the mechanism by which this particular molecule, phosphine, can be produced in the abundance that appears to be the case, a current living system seems to be the best explanation that people can come up with. So that's tentative. I mean, it's not very indirect. Nobody's scooped up some surface material on Venus and located microbes or anything of that sort. But think about how exciting that would be. In fact, I'm just curious, for those of you who are willing to share your thoughts maybe in the chat or something, do you think that there is life out there in the cosmos beyond Earth? That's big question number one. Is there life out there? And question number two is, do you think there's life in the solar system, be it Venus, be it Mars, be it Enceladus, Europa, whatever, the many places that have been suggested as possible forms for life? But the third and most important question, and I see most of you are saying, yes, life exists. Yes, we think it does, obviously, for question one, but it's not so obvious for question number one, right? I mean, it could be that life is this incredibly rare occurrence that even though there's so many planets around so many stars in so many galaxies, if you call that number n and the odds, the probability of the requisite conditions for life occurring, if that is much, much smaller than 1 over n, then it's not so obvious. But yes, I certainly share your intuition. I would have voted yes on question number one. But here's question number three. At least we have one no on question number two. Question number three, life is one thing. Intelligent life, a completely different category of life. I mean, they're seamlessly connected, but the discoveries would have a radically different impact. I mean, there's just so much of a conversation you can have with a microbe. It's an interesting and powerful moment in the history of scientific discovery to be certain that life exists on other worlds, but to be able to have communication and to share knowledge and heritage and insights about the nature of the world, to no longer be having what might be called a species-wide monologue right? We humans, we only talk to ourselves. I mean, yeah, some of us do talk to other, look, I talk to my dog, right? So I don't mean it in a very strict literal sense, but the kinds of communication where there's a back and forth, where the information is truly being shared as equals, we tend to do that only from human to human. And if we could do that human to other species on other worlds, wow, right? What an amazing moment that would be. And more than that, here's the thing. All life on planet Earth shares basic structures, shares the basic way in which genetic information is stored in DNA. It's the same code, the same codons across effectively all life, the same energy extraction mechanisms, the same energy distribution mechanisms for the most part. I mean, there are some outliers, but for the most part, it's all the same. It would be spectacular to come upon extraterrestrial life in which it was just completely different, some different method of storing information that has been built up over the course of species. Or maybe there isn't even an information storage mechanism. Maybe it's completely different. I don't know. But that would really be the most amazing thing. So yeah, so that's exciting news. Who knows if it'll stand up to further scrutiny, but that would be a wonderful moment if we could really locate life on another world like Venus. And I should say, you know, it's a course I teach where I have the kids read a Ray Bradbury short story. Ray Bradbury always was ahead of the curve in thinking about the way the world is and might unfold. And I don't know if you've read this short story. I think it's called The Longest Day. Anybody read that short story? Ray Bradbury fans out there read The Longest Day? I think that's what it's called. But it's a story where the explorers are on Venus and they set up, you know, colony, and they've been there for a long time. So virtually none of them have a memory of planet Earth. But then an interloper from Earth arrives and joins a classroom. A schoolgirl joins a classroom. And the sun comes out once every 7 years on Venus. And they're all preparing for this miraculous moment where the clouds and the rain, the incessant rain, will finally clear away. And this one student, this girl who'd come from Earth, you know, a while back, she remembers what the sun is like, and the other students are all jealous. So they lock her in a closet for this once in a 7 year appearance of the sun on Venus during this like 1 hour respite from the rain and the clouds. It's kind of a wonderful story. So you should check that out. All Summers in a Day. Yeah. Thank you, Raina Pratap. I had the title wrong. It didn't sound right to me, The Longest Day. All Summer in a Day is that story. Absolutely. A hat tip to Raina Pratap. I appreciate that. All right, so let's get to some questions if you have any. Physics, math, universe, anything at all. I seem to have driven everybody into a direction that's somewhat off topic. All right, so some weird questions. Tribe Sale, does death hurt, like physically to the dying? I presume it depends on the method by which death arrives. So I don't really have a whole lot to say about that. What else do we have here? Susanth Durgaraju, can you explain Calabi-Yau manifolds? Sure, vaguely I can. In fact, I don't know, maybe we can even bring up a picture of a Calabi-Yau manifold while I'm giving this explanation. That's always fun when we can do that in real time. But Calabi-Yau manifolds are a mathematical description of the extra dimensions that naturally come from string theory. So many of you are familiar. We've been trying for decades to realize Albert Einstein's dream of a unified theory of physics. And many people, I'm included in that, think the most promising proposal that has been developed in, say, the last 50 years is this notion that the fundamental constituents of matter are not little dots, they're little vibrating filaments. And that small change, this is the amazing thing, right? That small change from a dot-like particle to a vibrating string-like particle. If the string is small enough, it looks like a dot. That little change winds up allowing us to put gravity and quantum mechanics into a consistent mathematical framework, which has been the stumbling point for a very long time in trying to come up with a unified theory of physics. Okay, good. But here's the thing. When you study the mathematics of string theory, you find kind of amazingly and remarkably, and to some, this is the death toll of the theory. For some, it's the most amazing insight of the theory. Depends on your perspective. But the math requires that the universe have more than 3 dimensions of space if string theory is to be right. So we all know about left, right, back, forth, up, down. It's like the dimensions are around me, they're around you. We move through them freely in day-to-day life. Those are the familiar dimensions of space. The math of string theory demands more than those 3 dimensions of space. So the natural question that we've struggled with for a long time is, okay, right, if this theory has any chance of succeeding, we better explain where those extra dimensions of space are. Where do they reside? And one answer, and look, this is what I worked on as a graduate student, and it's been around for a long time, is this. So you got the 3 dimensions of space, which are like this grid here. But if you go smaller and smaller and smaller, according to these ideas, you find extra curled up dimensions, right? So this animation shows dimensions curled up into the shape of a circle. That's just for ease of visualization. And the idea is, if a microscopic being is walking around in that environment, they'll know about the big dimensions that you and I know about the grid. But look, the microscopic being can also walk around the curled up dimensions, so small that we don't see them. But the math of string theory doesn't say that the extra dimensions are these little circles. And now we come to the question that was asked. This is the kind of shape that the math of string theory seems to require for the extra dimensions of space. And these are known as Calabi-Yau manifolds. There's math behind this. These are complex Kähler manifolds of vanishing first Chern class. But, if math is not your thing, that's fine. This picture is really worth whatever. I've almost said 1,000 words already. This picture shows the shape, a possible shape for the extra dimensions in string theory. And those beautiful curled up components of space represent the extra dimensions, the Calabi-Yau manifolds. Now, when I was a graduate student, when I was starting out in the 1980s, when my hair was dark and the hairline was further down, looked like a young man. And thank you for all these who remind me that I'm aging, as we all are, frankly. But when I was a young man, we only thought, the very first paper written on Calabi-Yau manifolds only had 5 examples. I showed you 1 picture. But there were 5 known examples of Calabi-Yau manifolds. And the beauty is that the math of string theory linked very precisely the shape of the Calabi-Yau manifold with the physics that we would observe, like the mass of particles and the strengths of particular forces, depending upon the size of the Calabi-Yau manifolds and so forth. So the dream was, and in some sense still remains, that if we knew the exact shape of the curled up component of the universe, we could use that shape to make mathematical calculations of physics in the world that we can observe. So you can't observe the shape directly, it's too small, but the shape casts a shadow into the realm of physics that we have access to. That was the idea. So as a graduate student, I and a couple of friends of mine, Kelly Kirkland, Paul Myron, our advisor at the time, Graham Ross, set out to calculate for a given shape of the extra dimensions, the physics that we might observe. And we picked the most promising of the known shapes at that time, and the physics that we extracted wasn't so distant from what we observed, but it was not really possible to do the calculations with enough precision and to link things up precisely. And it was awkward. It was tricky. You had to jump through hoops to make this particular shape, I should say, compatible with the physics that we observe. So the thought was, well, look, just go through the rest of the shapes, only 4 others at the time, and maybe one of those does a better job and is bang on accurate in its predictions of how the world actually is. The problem is, over time, in the 90s and 2000s, the number of Calabi-Yau shapes, again, I showed you that one beautiful purplish blue pinkish picture, the number of shapes has exploded. in terms of people mathematically discovering different shapes that meet the equations of string theory. So that now the number of shapes is not like 5, it grew to 1,000, then to 10,000, 1,000,000. It's exploded to numbers that are not astronomical, would be a paltry description. They're far bigger than astronomical. 10 to the 500 is a number that people kick around. And when you have that many shapes, obviously you can't examine them all. So some have viewed this as the collapse of string theory, because now there's so many different shapes and you don't know which is the right one, therefore you never can make any precise predictions, is the thought. But others like me say, hey, it's early in the game. We've been at this for decades, sure, but it's early in the game when you're talking about a theory that might address the deepest questions of the ages, right? Why the universe is the way it is, right? That's the big question of them all. So many of us just say, hey, we got to work harder, got to keep doing our mathematical research. You got to keep trying to find indirect ways to link up the unobservable qualities of string theory to the observable qualities of the world. And that's really where we're pressing onward. So that perhaps, Susanth, was a longer answer than you expected, but that's what a Calabi manifold is, the curled up extra dimensions of string theory, and that's the role that they play in our understanding of the world. Okay, Andrew Haney, sir, we are waiting for a general relativity course on World Science U by you. Yeah, I know. I feel guilty. I sit here with my head hung low. It's hard to put these courses together because I like to do it right. And look, one way I could do it, I could just do it completely informally at a board. I don't know. I just feel like I want to do it with the right visuals. I want to do it with the right interactive demonstrations so you can get a visceral feel for things like curved space and geodesics and the nature of curved time, warp time. So it's just a lot of preparation. But I am thinking that this fall, since I'm not going to be doing any traveling, obviously, at least I'm not going to be doing any traveling this fall, this may be a time when I can carve out the necessary time to get it done. So Andrew, it's not lost. It's just taking a little bit longer. But yes, it's on my mind. All right, Neil, World Science Festival, more physics panels, please. Dr. Brian Keating. Yeah, I like Brian Keating. He's great. When is the next World Science Festival? Good question, Neil. So we're going to start rolling out World Science Festival programs done, in our, look, we could have just knocked out the World Science Festival programs by having a collection of Zoom conversations replacing the stage conversations. But Zoom conversations, again, are just hard to watch after a while. They're kind of limited in their visual appeal. The content can be good, of course, but you know us, we like things to really be visually compelling and not for bells and whistles sake, but to really try to communicate the ideas in the most interesting and most impactful way possible. So we took a breather when we had to cancel the live 2020 festival and have been thinking about ways to bring programs out into the digital space that will have the same kind of impact, although it'll be different, obviously, but the same kind of impact as our live programs in theaters do. And I think we've come upon some pretty good ideas, and we're going to be implementing those in the coming weeks. So I don't know, probably by mid-October, we'll start to release World Science Festival programs, and I think you're going to find them an exciting collection of topics done in a way that is visually interesting and impactful. So that's the status of the World Science Festival, very much in production and very much on the verge of being available. So just hang tight, and all that cool information will become. In fact, I think the first program that we're going to release, if I'm not mistaken, is a program that examines the question, does math reveal reality? Right? Again, you guys can chime in on this. Is math something that we humans come up with in order to basically encapsulate the patterns of the world that we encounter through observation and experiment? Or is math out there? Right? Is math actually out there? And there are a variety of views on this. My view is more toward the former, that we come up with this stuff. But the conversation will be with philosopher David Albert, philosopher Shelley Goldstein, who have different views on these ideas. I mean, Shelley in particular, I understand, believes that consciousness transcends mathematics. So there's something in the world that is not accessible to the reach of mathematics, and therefore it's a limitation on math from his perspective. I do not agree with that, but we'll argue it out. We also have Max Tegmark. Many of you know Max through his books and various science for the public undertakings that Max does. And Max has perhaps the most extreme position that all math of any stripe is real. It's actually out there. So any math that you find in any textbook, anywhere, or any paper, however esoteric that paper might seem, Max would say, you're actually describing something not that came from the human mind. You're describing something that's out there in the world. And I look at that, I'm like, seriously? But yeah, he's serious. And he's got arguments for this, and we'll discuss it. And I will respond. And, philosophers like David Albert, if you know him from our other programs, David Albert does not suffer fools, right? And he does not take in, it'd be kind of interesting to have a debate between Donald Trump and David Albert. Man, that would be a major mismatch of the minds. Maybe it would be too much of a mismatch. Sort of like, I don't know, if Einstein was to talk to an ant about general relativity. That's not a bad analogy. Hope the Secret Service is not going to show up at my door now. But yeah, so how did I get there? So my point is that David and Shelley, and we'll be really pressing Max to see whether his argument that all math is real stands up to scrutiny. Sylvia Jonas will also be in that program, philosopher of math who has spectacularly interesting ideas about where math comes from and the role that it plays in human thinking and society. So anyway, that's the kind of stuff that will be coming your way in the very near future. Okay, let's see what else we've got here on the live chat window here. All right, there's just one that I like, but then I touched my screen. There it is. Rajav Anand, Professor Greene, can the imagination of the human mind be faster than the speed of light? Well, yeah. So there's no process in the human brain where information is communicated from place to place faster than the speed of light. But when you talk about speed, you better have a very clear sense of some kind of entity of some sort, starting at one location, ending at another location, and you are determining the distance that it traveled divided by the duration that it took to complete that journey. And if you're talking about the human imagination, it's not obvious to me, beyond the physical, biological, physiological processes in the brain. I don't really know how to measure a speed because I'm not in the context beyond the actual physical of the processes. I'm not in the context of something going from here to here, a duration in a particular duration. So I'm sort of not sure how to answer the question. Let's see. Arjun, can we compare 1 over 0 to singularities? And yes, I think that's a very good comparison. So oftentimes when we're talking about space-time and black holes, the general theory of relativity, the kinds of ideas that emerge, we talk about space-time singularities as a quality that can infect a solution to Einstein's equations. A black hole right at the center point, the r equal to 0 location. The metric, that is the distance relationships on that space, blow up. It's a singularity. And when we talk about that singularity, what do we mean? And exactly as you suspect, Arjun, the 1 over 0 is a pretty good model of what we're talking about. And when we talk about the curvature of, say, the black hole solution, right? The curvature goes like 1 over r to a particular power. I think it's r to the 6th. Don't quote me on that, but I think that's the right number, which means as r goes to 0, you do get something that looks like 1 divided by 0. So the curvature blows up in exactly the way that you suggest. So yes, that's right. Alexander Serebryansky, talks about -1/12 equaling infinity. And yeah, that's a curious fact that emerges in a lot of different areas of physics. Certainly in string theory, it plays a very prominent role. And what Alexander's referring to is, if I ask you the question, and many of you are familiar with this from YouTube, or I've seen it like as a meme on social media, but if I ask you to add up 1 + 2 + 3 + 4 + 5 to infinity, naturally we would say, well, that must add up to infinity, right? I mean, it gets bigger and bigger and bigger. But we in physics, and mathematicians more generally, often find a way of making sense of certain kinds of infinite expressions by fitting them within a larger rubric of ideas, where you don't just look at 1 + 2 + 3 up to infinity, but you look at something similar to that. For instance, imagine you look at 1/n⁻⁻⁻, as s goes from 1 to infinity. And notice when s is -1, 1/n is just n. So that function, it's called the Riemann zeta function. The Riemann zeta function at -1 is the sum that we were looking at. But the Riemann zeta function, you can evaluate it not for s equals -1, you can evaluate it for any value of s. And then if you're nearby to -1, you can take a limit as the parameter goes to -1 and define, if you will, the zeta function at -1 to be the result that you get from that limit. And if you follow that procedure, you find that the zeta function at -1 does add up to -1/12. And that's the way you can get 1 + 2 + 3 + 4 + 5 up to infinity to sum to -12. So it's kind of a weird idea, but that's the weirdness of infinity, and it's the way that you can tame certain infinite quantities. And yeah, in string theory, the quantum mechanical vibrations of a string winds up including that particular sum. And that -1/12, it turns out, if you multiply that by a half, it gives you -1/24. And if you flip that upside down, that -24 is actually turns into -26 from using the fact that you can have dimensions that are space-like and time-like. And if you take that all in stride, that's where the 26 dimensions of the bosonic string comes from. It's effectively -1/12 times a half, flip that guy upside down, subtract 2 from it, get -26, and then the 26, the magnitude of that, is the number of dimensions. And a similar calculation gets you the 10 dimensions of the superstring, the supersymmetric version of string theory. So yeah, these calculations really do matter. And maybe sometime I'll do an actual video explaining that. I can't imagine that what I described was clear unless you've sort of encountered it before. But the bottom line is certain infinite quantities can be defined in a way that's completely rigorous and sensible and gives them a finite value. Okay, so what do we got here on the, let me look on the list of questions that we got on here. So Udvash mainly asks a question that we will take up in just a little while, which is, what is dark matter? Is it an object? Is it a particle? Is it energy? Is it both? So yeah, that's a good question. It's dark, so we don't see it. We believe it's there by virtue of its gravitational influence, as we will discuss, but nobody can answer that question yet. That's the big question. Whoever answers the question, what is the dark matter? Or whoever proves that the dark matter paradigm is wrong and there's a new explanation and proves that explanation, they will be getting a trip to Stockholm. So this is a big deal, and that's what we will be talking about. Shrindi Cabra, please explain why string theory requires more than 3 dimensions. Gosh, I wish I could. I mean, I know why it requires more than 3 dimensions, of course, but to explain that in non-technical language has always stumped me. I mean, I can give the rough idea. When a string vibrates, okay, if the universe, say, only has 2 dimensions of space, so that string's vibrations are only, say, like on a flat tabletop, the number of distinct vibrations, of course, is less than if that string can also vibrate in a 3rd dimension, which is less than if the string can also vibrate in a 4th dimension or a 5th dimension. You can't picture that one, but you can get the pattern that the more dimensions there are, the more distinct vibrations a string has access to. And it turns out, in essence, that there's an equation in string theory that requires the number of distinct vibrational patterns of a certain energy, say, to equal a particular value for the theory to be mathematically consistent. So if you then start to examine a universe with two dimensions, like, oh no, it doesn't work. Math doesn't work. There aren't enough distinct vibrations for a string. I say, okay, well, look, let's go to 3 dimensions. We look around, there are 3 dimensions, and you have more, and you're like, oh, darn. Yeah, there are more vibrational patterns, but still not the right number, not enough to satisfy the constraint of mathematical consistency within string theory. You say, well, okay, well, look, let me be maverick about this. Let me think outside the box. Let me imagine there's 4 dimensions of space, yet more vibrational patterns of a string. Okay, does that saturate the equation? Does that meet the constraint? No, it's still not enough. And you keep on upping the number of dimensions, increasing the number of vibrational patterns accessible to a string, until it turns out wonderfully that when you get to 10 dimensions, it all works. The math comes together. And that's not obvious that there'd be any number of dimensions that would work, but it works. That's impressive. But then you're faced with the question that we started out with, which is, if you take this seriously, that the world has to have more dimensions of space, then you have to explain where those extra dimensions are. And that takes us right back to the question about Calabi-Yau manifolds that we started out with. So I can't explain why any particular number of dimensions is singled out by string theory. That's truly from the mathematics. But I hope that gives you some semblance of an intuition about why more dimensions are required. Okay, that's a good question. What else do we have? Martin Topinka from Prague. Can you explain how a photon can reach infinity and beyond in the conformal cyclic universe? Yeah, so again, it's a tough question, but distances in a universe are measured by something known as a metric. I mentioned it before in the general theory of relativity. And different metrics yield different notions of distance. And there can be certain metrics that are such that you can reach the infinity of space from the standpoint of, say, a Euclidean observer. They'd say that's infinitely far away. But this other notion of distance that comes from this conformally scaled metric can yield a finite distance. So it's basically the idea that infinity, in some sense, is in the eye of the metric, and it's in the eye of the person who commits to using a particular metric. And that's why you can have different notions of which part of a space are accessible versus those that are not. It's totally dependent on the way in which you measure distances, totally dependent on the so-called metric of general relativity. And certain metrics have counterintuitive properties, allowing you to, say, get to infinity in a finite length of time. Okay, let's see what else we have. What time is it? Oh, I should, well, now we have a little time. Let me just do a few more questions before we get to our dark matter conversation. Let me see what kind of cool things you guys are asking about. Let's see. Ankit Kumar says there are 56 dimensions according to the Vedas. Yes, Ankit. I sort of know that, not that particular number by any means, but I may have mentioned in previous conversations that my brother, who's a writer and a filmmaker, but he is also a Hare Krishna devotee, has been since the 1960s, before many of you were even born. And over the course, I mean, if you read my latest book, Until the End of Time, I do mention this in the nicest of ways. But basically, over the decades, anytime sort of we would find something interesting in string theory or physics, and my brother and I, who we have sort of sporadic conversations, we don't speak every day by any means, and there are long stretches when we don't have a whole lot of communication, but it has been interesting. It was more in the old days than more recently, that when we'd come up with some discovery, he would say, aha, We know that already. It's like in this or that Vedic text. So I was curious about this, and I did a little bit of research. I can't say I became in any way, shape, or form a Vedic scholar, but I was just curious. And the connections that I found that he was referring to, and maybe I misinterpreted. So if you guys want to correct me, please feel free. But the connections that he was largely finding were poetic connections, metaphorical connections. Like when we talk about the number of dimensions in string theory, it's coming from a rigorous mathematical equation that I tried to give you a sense for that equation in words, but of course, there's just so far words can take you. But when you see the various numbers and the various ideas in the Vedic texts, they don't emerge from that kind of a systematic, inevitable chain of thinking, as far as I can tell. So there is a poetic resonance between some of the ideas of modern physics and some of the ideas in sacred texts, which is kind of cool. It's interesting. But that cannot really be taken as a point of literal contact between the rigorous science and the more poetic, metaphorical, sacred text descriptions. Because look, I'm fond of saying, if you're interested in the magnetic moment of the electron, you can calculate that with quantum field theory to 10 or 11 or 12 decimal places. And there's nothing in any sacred text that I have ever seen that allows you to take insight about the external world and push it to that degree of precision. And so that's what I mean by these connections are lofty, high-level, poetic, metaphorical, whereas the connection that would get us fired up, I mean really fired up, if you go to an ancient sacred text and you're like, there it is. There's the calculation of that electron's magnetic moment. And there are all the digits right there in the sacred text. And here's how the sacred text came to that number. Wow. Then everything changes. But I don't suspect that will ever happen. And that's why these connections are interesting. And I find them beautiful. I find it beautiful that certain ideas that modern physics has found interesting and powerful, some of them have a poetic home in other ways of thinking about the world. That's cool. That's great. That's inspiring. But it's not as though it's the same. And that distinction is important to keep in mind. So someone named B says, why do we need calculations for it to be true? I'm not saying that you need calculations for something to be true. I am saying that different modes of inquiry into the world come with different yardsticks for success and different acceptable modes of analysis. And when you're talking about the scientific approach to the world, the mode of analysis is mathematics and careful observation and experiment and calculation that attempts to explain the things that we see with mathematical precision. That is one arena of human discovery and exploration. If you're interested in the kinds of issues that the world's theological approaches tend to focus upon, then your yardstick for success is simply different. It's not better, it's not worse, it's just different. And for most people, a religious perspective on the world is judged, if that's even the right word to use, it's often not, but is evaluated by the degree to which it feels right, the degree to which it enriches life, the degree to which it provides for some kind of notion of value or meaning or a purpose. And in that arena, no, you don't need to calculate anything. That's not my point that I was making before. My point making before is if you try to say these two modes of inquiry are in some sense the same, they're not, I don't think. But if you try to say they're the same because they both use the word vibration or they both talk about extra dimensions, if you try to say they're the same, now they're no longer distinct modes of human inquiry. And if they are meant to be the same, you should investigate that. You should interrogate that suggestion. And to interrogate them being the same means take the modes of one and see whether they are relevant to the other. And calculation is relevant to the scientific approach. And the point is making is not relevant to the theological approach. And that, to me, is strong evidence that they're not the same. There can be poetic resonances, but they're not the same. And that's the point that I was making. Okay. Aguilat asks, is our future and our present and our past, do they all exist? Do they all exist simultaneously? And look, the bottom line is I'm not sure. Nobody really is. But there are arguments that many of us find convincing that go really back to Einstein, that what one observer considers to be the present can be another observer's future, and it can be a different observer's present if these folks are all moving relative to each other. And so the subjective nature of the present and the past and the future suggests that the sharp demarcation that we usually make from the perspective of a single individual, I'm here right now, right? That's now. The clapping of my hands is now. Right? Sorry if I hurt your ears, right? The past, future, and sometimes bound this moment, but are not real or not as real as this moment. That's how it feels to me as an individual. But if the past is real to somebody else, and if what I call the future, I should have said what I call the past is real to somebody else, and if what I call the future is real to somebody else, if they're moving the right way, then who am I to say that my very subjective notion of what's not real holds any more weight than anybody else's subjective notion? So one way to deal with that is to say that everybody's subjective notion is on an equal footing. And if that's the case, then things that I call the past are real to somebody else, so they are real. Things that I call the future are real to somebody else, and therefore are just as real as what I consider to be real, which is the present. And that's what Einstein basically meant when he wrote to the widow of Michele Besso, right? That was his friend, that he had innumerable, deeply important, profound conversations over the course of their 50, 60-year friendship. When Michele Besso died, Einstein wrote to Besso's widow saying that, you know, he's departed this world a little ahead of me, but to we convinced physicists, the distinction between past, present. I'm going to say that again because I got a little getting choked up. Really, no, it just had a little catch in my throat. To we convinced physicists, the distinction between past, present, and future is only an illusion, however persistent. And that's again a very poetic way of saying what I was describing from special relativity. So in that sense, yes, it's possible that the past, present, and future all do exist together. Okay, so Zachary asked, how did we get DNA? It's a good question, Zachary, a vital one. And if you're interested in a more fleshed out version of the answer I'm about to give, again, get my book from a library. I'm not a salesperson for my book. You know me, I hate that kind of stuff. But this is something that I go into some detail in until the end of time, because I wanted the origin of the universe and the origin of life and the origin of the fine structures that life requires and the origin of mind. And then, of course, the cessation of all of those processes. I wanted that to kind of be put into a coherent framework. So that is something that I discussed. But briefly put, we're all familiar with Darwin's evolution by natural selection. But most of us learned that, I certainly did, in a biology class, in its relationship to the many species on planet Earth. So the question Darwin addressed is, how could there be such a broad range of species? And of course, the answer he gave is that over time, there can be mutations in the genetic makeup of a given individual member of a species. And if that genetic mutation makes that individual better adapted to survive in the environment, and that individual is better or more likely to produce progeny who will inherit that mutation and spread that mutation widely. And over time, the accumulation of many of these mutations can yield gradual transformations that ultimately result in distinct species. And if you allow this process to play out over, billions of years, timescales that are very hard for the human brain to fully process, then starting from some uniform beginning, you can imagine species branch off through these accumulated genetic mutations. Now, that's evolution by natural selection at the level of life. But as I emphasize in my book, and it's not my idea, but this is well known, there can be a version of evolution by natural selection, not at the level of living species. There can be a version of that comes in at the level of molecules. So in some sense, molecules can battle molecules in an effort, if I anthropomorphize, to gain access to the greatest amount of raw material in the environment. And so molecules can then mutate once they learn to replicate. This is the key thing that I should have stressed at the outset of this answer. Once a molecule learns the trick of replication, it can dominate the environment if it learns to replicate better than other molecules, faster than other molecules, more stable than other molecules. So over time, mutations in that replication process can yield ever better adapted molecules. And over time, those molecules and therefore become ever more complex. And when a molecule not only learns the trick of replication, but the trick of storing information, then that's an incredibly powerful molecule because it can hold on to the evolutionary lessons of the past, not have to reinvent the wheel. So that sophisticated molecule holds on to information that can then sculpt other molecules in the environment. And now we're talking about a replicating molecule that holds on to information. Does that ring a bell? DNA is an example, prime example of that kind of a molecular structure. So that's the way in which DNA could just have emerged through the natural blind processes of physics, sculpted by a version of Darwinian evolution right down at the level of molecules. That's an idea for an answer to that question. Again, if you want to see that in more, spelled out in more detail, you can check out Until the End of Time. And but that should give you a feel for it. All right, a few more questions before. So when will Priya, I'm going to bring Priya on in about 10 minutes. So Arnav, yes, you're chomping at the bit for that conversation. So Priya should be with us in about 5 or 10 minutes. Let's see. Cutie, Minotti, why does light always travel at the speed of light in a vacuum? It depends on the level at which you're asking that question. In some sense, the vacuum by definition is an arena that is homogeneous. It doesn't change from place to place to place. And therefore, there's nothing in that environment to influence light's speed. So if light travels at a particular speed at one section in one area, one region of the vacuum, you would expect it would travel at the same speed in another region of the vacuum because those regions are in effect physically the same. There's no distinction between them because of that homogeneity. More precisely, when you look at the equations of electromagnetism, Maxwell's equations, you find within those equations, disturbances to the electromagnetic field travel at a particular speed that comes out of the math. And that speed is independent of where you are so long as the environment is empty, so long as it's a vacuum. So our observations and our math all converge on exactly the same idea. Subham Sahu asks, what is the speed of dark? I don't know if you're referring, maybe you saw a YouTube talk that I gave some time ago that when my son was quite young and I was telling him bedtime stories about aliens traveling near the speed of light, he turned to me and asked the question, what is the speed of dark? So I don't know if you're echoing my 5-year-old's, well, he's now 15, so it was a long time ago. Yeah, the speed of dark, what is it? It's a beautiful idea. I was kind of surprised when my son asked that question. But if dark is the absence of light, then of course the speed of dark is the speed of light, because if light is leaving a region, it leaves that region at the speed of light. So the speed of dark, the increasing domain over which light is absent would be equal to the speed of light, which is the speed at which that light can leave that region. Let's see what else we have before we turn to dark matter. Priyamvada, one of our longtime stalwart attendees at these gatherings, asks a question, which is a good one. What is time symmetry? What is time symmetry? Well, it's almost easier to answer the question, what is time asymmetry, and talk about symmetry in response to that. But time symmetry is generally the idea that one direction of time and the other direction of time are on completely equal footing within our physical understanding of the world. And that's a weird idea, because if you think about your life, thinking about the future and thinking about the past, those are completely different temporal arenas. The past usually you think of as it's gone. It's like set in stone. It's finished. The future is open-ended, has yet to occur. You can remember the past. You generally don't remember the future. You have the opportunity to mold the future. You don't have the opportunity to mold or affect the past. So from an everyday life perspective, there's a big difference between past and future. But, you know, if you studied any physics at all, even the most basic equations of physics show that there's no difference between past and future. Past and future in physics basically amounts to replacing a variable called t, the time variable, replacing it with minus t. That's it. Positive t going this way, negative t going that way. And the equations that we have are generally insensitive to that replacement. The equations don't care whether you're using them to start from this point in time and use the equations to predict what things will be like, or to post-dict what things were like in the past. The equations don't care. They don't make a distinction between those two, and yet we do. So time symmetry is the mathematical fact that the basic laws of physics as we understand them don't seem to show a distinction between past and future, and that's puzzling. And we have to try to explain why it is that we as human beings absolutely do see that distinction. Okay. Sorry about that. I think I did not bring enough water today. So if there's anybody in earshot of this plea for more water, that would be great. If water could show up at my door, socially distanced. No, it's only my family here, so we don't have to worry about that. Okay. John Olson asks, artificial intelligences are currently generating realistic images without having to calculate movement of every single atom. Is it possible that reality is already simulated by an AI entity? Of course. Yeah, that's the simulation hypothesis that we've spoken about from time to time in this gathering. And yeah, I mean, a sufficiently powerful computer, AI, whatever words you want to use, could certainly cause us to think that we are in a physical world populated by particles and atoms and molecules, when in reality, all that's happening is we're being stimulated by the simulation into thinking that the world as we typically describe it is real, when it may not be. So there's not a whole lot you can do with that simulation hypothesis beyond, you know, feeling a bit, you know, upended, feeling your world is undercut, you know, glancing around and wondering if the simulator is ever going to make himself or herself or themself visible to us. But yeah, is it a possibility? It is. I don't go around my daily life really worrying that I'm living in a simulation, but I do allow for that as a real possibility. And that's about the best that we can say about such things at the moment. Rob B, do you fear the singularity? No, I don't fear singularities. I hope that they're kind of far away. That would be a happy state of affairs. Oh, good. My son is bringing me water. Yes. But I don't fear it. I don't stand in tremble at the possibility that there might be some space-time singularity. Rather, my view is, and I think this is the view of most scientists, singularities are the big opportunity of, say, theoretical physics, maybe observational astronomy too. They're the big opportunity, because if we can learn how to cure mathematically certain space-time singularities, that may represent a deep advance in our understanding. And so, some of you know, I was fortunate to be involved in some work a while ago that showed how string theory can cure certain kinds of space-time singularities. These are singularities that would arise if space were to rip in a certain very specific mathematical way. And so that perhaps fearful possibility of space ripping, we neutered it, right? We showed that it could be cured in a way that doesn't have any dangerous physical consequences. Again, within a very specific theory, specific kind of rip. But that's the general way that we approach singularities as theorists. Okay, great. Let me do one more question, and then we'll get to our dark matter conversation. Okay, what do we got? How do stars form? Good question. Gravity basically pulls matter together until the density and temperature are so high that nuclear processes ignite. So that's a quick one there. Lion King. Could a black hole be stabilized after almost fully evaporating via Hawking radiation? Yes, this is the idea of remnants, black hole remnants. I don't think most people take that idea that seriously these days any longer. I mean, some do. It's possible. It's definitely out there. But yes, it's possible that a black hole could evaporate, get smaller and smaller and smaller, and then it stops. And what's left is a little tiny nugget. And that little nugget might be the endpoint of black hole evaporation. Absolutely a possibility. Do gravitons exist? Somebody asked. I don't know. If the traditional way that we think about quantum mechanics, if that has relevance in a theory of gravity to make a quantum mechanical theory of gravity, like string theory, then gravitons would exist. But if there's a different way in which gravity and quantum mechanics talk to each other, and it's not that you quantize gravity, but rather you gravitize quantum, whatever that means. If the sort of gravity is dictating the story, maybe gravitons don't exist. But I'd say most people who work on quantum gravity would answer the question, yes, that gravitons do exist. Avdut asked, does cause and effect, is that invalid in quantum mechanics? And no. The cause and effect is alive and well in quantum mechanics. You have to be very careful about the causes and the effects, and you have to be careful in analyzing the processes because they're different from the Newtonian classical processes. But if you think about a quantum mechanical wave function, it evolves in time via a deterministic equation called the Schrodinger equation. And that deterministic evolution takes how things were in the past, feeds them into the equation, and that then, in that causative manner, determines what that wave function is like in the future. So, yeah, there's a version of cause and effect. There's a version of causality that holds perfectly well in the quantum mechanical description of matter. Rami Alsbog asks or says, I miss your daily equation. Yeah, I know. It was fun to do that, for a while. But to come up with a new equation every day and then to sit down and do a little discussion of it, it might sound like it's trivial, and at some level it is trivial to do. But when you have a lot of trivial things to do, and I have a lot of other trivial things that I have to do, you wind up realizing that your whole life is being eaten up by, I don't mean trivial in the sense of, trivial that it's not like useful and important. What I mean is trivial in terms of a time sink. So don't get me wrong, that's what I meant. But when you have a lot of trivial things, a lot of little time sinks, they add up to a major time sink and you wind up getting nothing else done. So that's why I had to sort of wind down and retire the daily equation. But maybe I'll be energized at some point soon and we'll come back to it. All right, I think with that, let me just take another sip of water here and turn to the main headline event, if you will, of our gathering here today, which is this discussion of dark matter with Priya Natarajan. So Priya is someone I've known for a long time, great physicist. She's a professor at the Department of Astronomy and Physics at Yale. Great place. She's a theoretical astrophysicist who's interested in cosmology, gravitational lensing, and black hole physics. And just recently wrote a really interesting paper on dark matter that we're going to be discussing. Let me bring Priya into the discussion now. So if Priya can join us, I think Priya, yes. Priya, do you see
Hi.
me?
Yes,
Hey.
do you see me?
As I can. Great to see you. How are things going?
Good. It's actually my sabbatical year, but my wings are clipped, so I couldn't go very far from New Haven. So
They're either COVID clipped or something else.
yeah, COVID clip. Yeah.
Yeah. And so where are you then at the
So I,
moment?
I went far. I'm in Cambridge, Massachusetts.
So you went like an hour or two away, something like that.
Yeah.
Are you at a university there?
And no, I was supposed to spend some time at the Black Hole Initiative at
at Harvard.
Yeah. But nothing is happening at the moment.
Yeah, right.
There are remote seminars, but no in-person. And
Right.
I haven't ventured to go there. I have allergic asthma, so I'm a little nervous.
Yeah, no, be careful with that.
Yeah.
Like, my son has an autoimmune disorder, so like we're being incredibly careful because of that. So obviously not anything to mess around with.
Yeah.
I mean, do you get out at all? I mean, do you? Yeah.
I get out for walks and runs. And the nice thing is that where I'm located, I'm pretty close to the river. And so I go out for walks and it's
Charles River.
Yeah, it's not actually been easy. So I actually live on my own, so I'm kind of used to my own company. I'm very social, but this is hard because this is sort of not self-imposed exile, but hermithood due to circumstances. And I really miss the thing I love is I love to cook, so I love to have people over for dinner, and
it's harder. It's harder. There was another, of course, many physicists have turned to, the Black Death, the plague of the late 1600s as the model, right? Because Newton,
yes.
Newton goes away, goes into isolation, and reemerges with the universal law of gravity. So all of us are like, this is our Newton moment, right? This is our plague, where we're going to disappear and come. But you've actually, I can't say that I've come forward with anything like that. But you wrote this great paper. It was just published like a couple days ago, right?
Right. So first, I rolled my eyes big time for those of you who didn't catch it with the Newton, the plague comment. I mean, the way we sort of valorize this stuff is just crazy, right, Brian? Yeah, whatever. But we had a very exciting paper.
Hey, we have to have our myths, right? Every tradition has got to have its mythic heroes and figures that inspire us to go forward. But yeah, I agree. When you examine any of these, or not any, but many of these stories, you examine a little more deeply, and they're not quite the story that you were told as a kid. But,
right. And also I would personally feel more comfortable if there were a few more like heroines around. There's always that niggles me. That greatness doesn't seem to stick to our kind as easily.
Yeah. Well, hopefully that's changing.
Hopefully.
Certainly the history of most sciences is not an emblem, is not to be held up as the model of the way that the world should work.
Right. So coming back to our paper, so it's a paper that's led by Massimo Meneghetti, one of my collaborators. And we found something really sort of surprising. But, I've been on the trail of this for a while. So the idea is that, we see gravitational lensing, sort of the bending of light by some of the most massive structures in the universe. You see it very clearly for clusters of galaxies. And the idea is that, in our theoretical framework, we know how these clusters form, and we can now form them in these simulations in the box. So we can simulate a piece of the universe and we let it go, and you can form pretty much all the structures that you see. That's how successful the model is at the moment. So what this allows you to do then is to directly confront the observational data, what you infer from the data, with your simulated universe. So you can make a mock observation which mimics your real observation and then see how do they tally. And so I had been trying to do this. And, sort of so first thing you have to do is you have to conceptualize a cluster and observed real object in the universe in such a way that this comparison is amenable, that you can actually compare with simulation. So that I sort of wrote a paper. Actually, it's one of my first papers in grad school. And I'm going to date myself. I hate to do this, but you can go look it up. So I might as well declare. It's 1997. I was a young graduate.
Heaven forfend, you were a graduate student in 1997. But
that was my first year or so. Okay. So, yeah. Okay. So, and so the idea was that the conceptual model is that you think of a cluster as a huge lump amount of dark matter, like a mountain range, but then that there are individual peaks. And the reason for that conception was that, most galaxies have their own individual halos of dark matter. They have their own glob of dark matter associated.
Can you explain that? I mean, there's some folks who will follow everything that you're saying, but do you mind if we even unpack some of the ingredients as we go along? So you're talking about galaxies and dark matter. Yeah. So like, where does that, I mean, just can you give us a little bit of history of why we even think that there is dark matter in galaxies?
Right. So I think there's a pretty rich history for this, right? So I think it goes back to the 1930s with Fritz Zwicky, this cantankerous Swiss physicist at Caltech. What he did is he measured the speeds of galaxies in a cluster. So a cluster of galaxies, oh, that's right. That's the iconic picture of him. Yeah. So galaxies are held together by the gravity of the cluster and they're moving around. And so in the Coma cluster, which is a nearby cluster to us, he went and measured the speeds, I think, of about 12 of them. And he found that they were whizzing around really fast. They were whizzing around so fast that it didn't make sense that they were still held by the gravity of all the matter that you can see. So you see stars and you see stars in these galaxies. And he said, well, there's something funny going on because there has to be some missing matter here because there's more gravity that is holding them in their grip. Yeah. The galaxies, they would fly off otherwise. Yeah. And so he proposed this term, Dunkel Materie, so dark matter, and that stuck. So he just said, well,
do you know that term actually goes even further back? We did a little.
Is that right?
Yeah, like I think we may even have it. I think Poincaré, if I'm not mistaken, made reference to. Do we have that Poincaré reference?
Matière obscure.
The translation of that. So yeah, it's actually an idea that goes even further back. But you're right. I mean, I think most people would credit Zwicky with the first time. And the only footnote that I just want to put into that story because his daughter contacted me after one of my books because I think all of us have this view that has been, again, maybe it's one of those lore like Newton and, during the plague coming up with, brilliant ideas. She thinks we're being very unfair to her father when we show that image.
Yeah. No, I
yeah. Do you know her? Do you know his daughter?
I don't know her, but I have to say that I actually admire him. I mean, I say cantankerous because that image, I knew you were going to pop that one up. And no, I mean, the thing, as a first of all, right, I think Zwicky was the first one who mentioned this dark matter in the context of a cluster. Yeah. Poincaré was in the context of the Milky Way, right? Yeah. So, he was brilliant in terms of the number of ideas he came up with, right? And of course, some were crazy and out there, but the hit rate was very good. And we forget that. I mean, this whole idea of supernovae and what you're seeing when a supernova goes off and tying it to the end states of stars, that's remarkable. Yeah. We wouldn't have found dark energy without that, right? I mean, so he has made enormous contributions. Right. I totally agree that, we tend to get sort of fixated because that images are so powerful. That's why, right?
Yeah. Yeah. I mean, the phrase that I remember that he is, whenever you see Zwicky quoted, they always quote the phrase spherical bastard.
Oh my God, I can't even.
I've never heard. We're allowed to say those words. Oh yeah, that's actually even. I think it's one of the 7 allowed words, even on any network. But the idea here is that apparently he would say, "What is a spherical bastard? It's a bastard when viewed from any angle." So these kind of, and now I'm propagating the exact same. I need to pull back and say this is what is typically said. But you're right. I mean, look, any human being's a rich collection of events, histories, quotes, sayings, insights. and his insights are deep.
No, but I think his daughter has a point that, as a very important point to make. First is the damage to his actual reputation.
Yeah.
The second is, as you just pointed out, right, by repeating this, Brian, somehow physicists in our heads, we also start to associate, you know what, you can be a jerk as long as you're brilliant. And we need to break that too. Because you don't have to be. I mean, there's no need for that allowance. But anyway, coming back to the dark matter, so he made those measurements, and he said, okay, there's probably, and he figured there had to be a lot of dark matter. And he wrote this paper. It's kind of sunk without a trace. Nobody took it seriously. They thought it's a bit too out there. And and in astronomy, right, we've also had a pretty checkered past and history with invisible entities like ether, which went away.
Yep.
So people were like, well, whatever, this invisible stuff, we'll see. But then, he was relentless. That's the other thing that I do like about him. And so he realized the further implications that if indeed there was so much matter, so this was the 30s, so Einstein's theory of general relativity was proven and, was the star theory. He said, then it would have to bend light, because any glob of matter in the universe actually bends the path of light, because
in fact that's how general relativity was first, the first major confirmation was bending of distant starlight by the sun. And you're saying that any source of gravity doesn't have to be the sun. It could be this dark matter. It acts like a lens.
That's
right. Light travels through it. The gravitational pull of that dark stuff pulls on the light itself.
That's right.
Yeah.
And I think you had a really beautiful demo that I remember. I think it was on YouTube, right? So this whole thing with space-time and the warping of space-time, the potholes in space-time due to matter. Didn't you have this like trampoline or something?
Yeah. We built a version of the spandex, gravity simulator, and we actually set it up in our living room at home. So it was with my two kids who were much younger.
I remember. I was going to say that you had sort of you had a little bit of child labor in you.
I did. In fact, my daughter was charged with putting the sun in the middle of the space-time simulator, but she was too little to reach. So I remember in the video I had to pick her up, reach that, and put the sun down there in the middle. But yeah, that is, and it's not. Look, I mean, people often ask me, how good of a model is that? And it gives you the mental toehold, but the reason why the simulator and the spandex warp when you put a shot put in the middle is because Earth's gravity is pulling on the spandex. So of course you're using Earth's gravity to explain the warped space, which is meant to be gravity. So it's kind of chasing your tail a little bit. But yeah, I mean, the basic idea, as you're saying, is when matter or energy is in space, it warps the environment. That's Einstein's idea. Not because something is pulling on it. It's just a fact of the way gravity works,
Yeah. And so, I mean, I think, as you said, right, one of the places where that analogy kind of gets a little fuzzy is the fact that it's hard for people to understand that, that is the entire universe. There's nothing above it, below it, because when we demonstrate, we're showing it in air or whatever. So we are all embedded in that space-time. So light has no choice but to propagate through every bump and wiggle.
Yeah. In fact, Priya, I'm just wondering, guys, can we bring up the 3? So there's a 2D version of
cool.
Space that you can see there. So you got a distant star, that's what you were referring to, and then the starlight is going on that curved trajectory near the sun. I'm just wondering, can we bring up the 3D version that we've made of this, where you see matter moving through a 3D environment? And maybe that can be brought up at some point as we're talking, because I think I have found that image really propels people's understanding because of the question that you just raised. It's like there's why under? There's like not to
exactly or above, right?
Or above or the side. So it's actually all around the object that space is being birthed. So if we can bring that up, if we can grab a hold of it, that'd be great. But yeah, going forward from there.
I mean, this light bending. So he said, okay, there is this other prediction for the nature of distortion of space by matter. And so he said, okay, let me calculate the light deflection. If indeed the coma cluster had the kind of mass that I think it does with the dark matter, he said, let me calculate what the light deflection would be. It is finite and it is calculable, of course, but it's tiny. And it was beyond the remit of telescopes at the time. Remember, like 100-inch was like state of the art at that point. Right? So, speaking of which, Mount Wilson, which is in peril right now with the Bobcat fire, do you know?
Oh, I did.
The fire is looking very close.
Oh my God. Really?
Close, yeah.
Huh.
But Anyway, the oh no, maybe it's not Mount Wilson. Maybe I'm getting it wrong. Maybe it's the Lick Observatory, Mount Hamilton. I think I
Yeah,
have my
yeah.
mountains wrong
Mount
here.
Wilson was Hubble, yeah. Either
So
way,
anyway, the so he then said that the deflection was too small, but so that was not persuasive either because it was not detectable. So kind
yeah.
of sat around. The idea kind of sat around, but then completely, as is apt to happen in physics, as you know, right? We keep rediscovering things that others have come up with and often don't see the connection. So Vera Rubin and Kent Ford were looking at a completely different set of systems. So they were looking
What year are we now, roughly?
at 70s.
Okay.
So I think during her thesis in the late 60s, she was trying to understand rotation of galaxies. Like, do galaxies actually rotate? What powers their rotation? And then later she started working in Washington at Carnegie DTM, and so with Kent Ford. And Ford has built the spectrograph, which allowed a new kind of measurement, which is a measurement of the speeds of stars inside a galaxy, like a spiral galaxy, from the center out. And I think you might have a visual for that.
Yeah, I think we do have a visual of spinning galaxies. If we can bring that up, that would be great. And the idea of the visual, if we get to it, here it is. So I guess it was Kent Ford's measurements that could give you the speeds of the stars in that rotating galaxy. And I gather the punchline, which we have in another visual, is that they're moving too fast.
That's right.
Yeah, and so they should be being flung outward like bicycle. The water drop is on a bicycle rim as it spins. The water flies off, but they're not being flung outward. So I gather they came to the conclusion there got to be some dark stuff there, giving rise to extra gravity.
Super, and yeah, I mean, and Vera Rubin charted what are called these rotation curves. So that's the speed of stars as a function from the distance of it, and so. Vera and Ford looked at them, and they looked really peculiar. They looked like it looked like the stars were being held up on the outside somehow.
Right.
The speed, instead of falling, there didn't seem to be kind of an edge to the galaxy, as it were, in terms of gravity. I mean, there was an edge in terms of light. You run out of stars, but and they sat on this paper. I spoke to Vera. I knew her quite well. She was amazing. And she would tell me that, they sat on this. She sat on this for years because
Really?
2 years, because they waited to gather more and more data. So they wanted more and more convincing data. So it was not a one-hit wonder for this one peculiar galaxy, right?
Yeah.
And then they went ahead and published it. And the implication was that there was some unseen matter, again, factor of 10. But, I went back and looked, and I even asked her, and she said, they did not connect the dots with Zwicky because that was a cluster of galaxies. They didn't think it was the same dark matter at that time when they were working on it. Of course, the connections were made soon after when theorists jumped in, and this whole cold dark matter model was proposed, and that accounted for the dark matter both on the scales of galaxies and clusters, and this whole idea that dark matter is basically smeared everywhere in the universe very lightly, and then it lumps in locations, and those are the locations where you preferentially form galaxies and galaxy clusters and so on.
So when we think about a galaxy, I think many of us have a mental image that's similar to the little animation that we showed. But if you include, as you say, dark matter, if you make it visible for visualization purposes, then the edge of the galaxy is completely different from what it is. So do we have a little image? I think we have an image of a galaxy together with the dark matter component made visible to get a sense of the
scale,
the kinds of scales that we're talking about. So if we can bring that up, that would be great. But the idea is, if you think about all the stuff, visible matter and dark matter, the scale of a galaxy can be much, much larger than simply the edge of the spiral arms.
Yes, right. Absolutely. It's almost, roughly speaking, it could extend almost 10 times, right?
10 times larger. I think we do have that visual someplace, so maybe it will come up in just a moment. Okay, so now we're at a stage, by sometime in the 70s, you've taken us through 30s, Zwicky puts forward this idea that's largely ignored, that there may be some dark stuff out there important for the understanding the motion of clusters of galaxies. By the 70s, the idea is out there that to understand the motion of individual galaxies, there's also some dark component, dark stuff, and people begin to think about those as the same stuff, that there is this dark stuff that's threaded throughout everything.
Yeah.
So then the natural next question is, like, what is the dark stuff made of? When do people start taking that question seriously?
1978 onwards, sort of theoretically, people started to see how could we explain observations on these various scales where this dark matter is showing up. And there was a little more sort of a deeper understanding of, star formation, galaxy formation by then. And then the idea was, how do you integrate the formation and the structuring of the universe that we see with this unseen component? So I would say that, the heyday was kind of 80s. And people started to do little simulations. So make up mock universes to see how this dark matter would cluster. And so as people started doing, so one of the things, the cool things and about this cold dark matter model is that, this model was refined along the way as we got more and more observations, right?
Yeah.
So Geller and Huckra mapped out galaxies in the very nearby universe. And I don't know if there's a stick man, they found that galaxies are clustered.
Yeah.
And so they're like, okay, so that's something that the theory then has to explain, what is clustering and what's going on, right? So they were able to then incorporate the data as it came along and refine this model. And this model, therefore, has, storyline of how you start from some initial conditions, and then, but that calculation of starting from the initial conditions and getting down to sort of the relic radiation, that Jim Peebles did already in the 60s. So the cosmic microwave background, and the fact that the microwave background that is now streaming towards us would inevitably encounter all the galaxies and everything that's forming in the universe en route, because these things form later in the universe, right? And so, all the pieces were kind of there already. And then there was this sort of grand integration, I think, sort of, it's a way to put it, that all the pieces came together. And so then we had this theory. But then this theory requires, to explain the observations, right? The theory requires that this dark matter interact only via gravity, that it has no other interaction. It's inert.
So no electric charge, no strong nuclear charge, no weak nuclear charge. The only way that it talks to particles in its vicinity is through gravity.
Right. And then the other,
and otherwise we would have seen it. Like, those are the constraint. That's the kind of consideration.
Right. And so, and the other key thread, as I said, right, there was this kind of collection of things that kind of made sense together. So from the particle physics end, the other thing that came in is that, astronomers were able to do an inventory of how much dark matter you have. How much do you have to have today? The question then is that, on cosmic scales, we cannot single out the behavior of a single particle of dark matter, right? We're looking at aggregates of dark matter and how they behave. It's cosmic scales. Whereas particle physicists are looking at, what is this particle? When was it made? And then it became clear that in a standard model of particle physics, which was also being developed along roughly the same time, it was clear that it was permitted. You could have many particles that are produced very early in the universe that would give you the right density of dark matter if they were dark matter. So they're like, bingo, right? We've kind of narrowed it down to candidates. And so we all became fixated, including myself, on neutralinos, as a favored WIMPs. So these sort of weakly interacting. So, you permit very weak interactions, if at all, but massive particles. And so, then of course, you have to do both things, right? So we have all been astrophysically pushing to look at the collective behavior of dark matter. And particle physicists have been looking at direct detection, trying to actually nail down the particle. So, those two threads have been going on.
And how much of this dark stuff should there be? How does it compare to the amount of visible stuff?
So, if you kind of do like a pie chart of all the matter in the universe, about 90%-ish, 94, 95% really, 90% should be dark matter. So we're dominated by dark matter.
Dominated by dark matter.
Totally dominated.
Now, and often when people show pie charts, and I think we do have a pie chart, we also wind up thinking about dark energy. So I know this is not our focus here today, but just so that this pie chart is clear, can you just tell us what briefly what the dark energy part of this pie chart is.
Right. So this pie chart is a full inventory of everything in the universe that counts. And so, the dominant component in this blue part of this diagram is dark energy. And this was dark energy was detected in 1998. And we believe it is what powers the accelerating expansion of the universe. At the moment, we believe that it could really be a property of space itself. We really don't know what it is. The nature remains an open question. We have some ideas and they're being actively pursued, but what we know is that it is the dominant constituent of our universe, and that it does something quite intriguing compared to matter. So, when think of matter, and we're going on about gravity, which tends to aggregate, it's an attractive force. Whereas this dark energy is sort of this repulsive thing because it causes the accelerating expansion of the universe. It's almost like space, the stretching of space. There's an acceleration of that expansion. I mean, just like, when you drive and you have to accelerate, you have to press the gas pedal and you have to provide some energy. So the moniker dark energy, and what it is, we have no clue.
But the main part for our conversation, if you can leave that pie chart back up for half a second, the main relevance for us is that green wedge is like more than 5 times the orange wedge.
Yes.
So we pride ourselves on the depth of our understanding of how material objects behave in the universe. We have the standard model of particle physics. You made reference to it. We can do these very, very detailed, precise calculations. But all of that is focused upon that little orange slice of the pie chart that you referenced. And that big green wedge, we don't know what that matter is. We don't know what equations govern it. We don't understand precisely how it talks to the other wedges in the diagram. So that's a great opportunity for us to go forward. And the point that you're making is there are candidates that people have put forward. My very first paper, you spoke about your early paper. My first paper was on a dark matter candidate. I'll date myself now. So that paper was not in the mid 90s, but in the mid 80s, so my first paper is in the mid 80s. And it was about a particle that naturally emerged in certain approaches to string theory. So we did the standard analysis to figure out how much of that particle would remain today if it were the dark matter candidate. And as you were saying, it's not that hard to write down models where particles from the Big Bang era would persist until today with the right abundance to be that green wedge in the pie chart.
Exactly.
And for many of us, and many of these are so-called supersymmetric particles, and some in our audience will recognize that word, supersymmetry. But for many of us as theorists, way back in the 80s, when this was sort of first recognized, it was remarkable that particles that were coming from theories that had nothing to do with dark matter.
Exactly.
And you stuck them into your calculations, and the amount that would remain today was exactly on par with what you needed for dark matter. This was so convincing.
Totally.
To so many of us.
I'm still convinced, but because we haven't, there are many candidates, and maybe we haven't been as open-minded about exploring that space. But can I share a little secret?
Yeah.
I almost did string theory and was going to work with Wafa, Kamran Wafa.
Oh, okay.
But I didn't, because I was prepared for it. Like I was an undergrad at MIT, did pure math and physics as majors. And, I was like the prime candidate for that.
Yeah.
Kind of work at the time. But you know why I didn't do it? Because I did not like the fact that you could not confront observations to test it. And
that's a good reason.
Vafa
was on the previous.
Yes, I know. And I think for me, actually, I was this like intense kid, right? So for me, it was like an existential crisis. Yeah. I actually took a break and I started a PhD in history and philosophy of science.
Is that right?
Yeah.
I don't know if I knew that background. So was it? So you were at Harvard. I should know all the background.
No, MIT. No, I was an MIT.
You're at MIT. Okay. You're at MIT.
STS. MIT.
Got it. Okay.
But it was twofold. First was that I was one of those kids who took like a million courses, were way ahead, did all the graduate courses. So I was ready to do research by the time I graduated. Incidentally, I did my undergraduate thesis in particle physics with Alan Guth, finite temperature field theory.
Oh, good.
calculated a Mickey Mouse diagram. So,
Nice.
but tiny little, nothing major, guys. No one should get impressed. I mean,
Great.
it was just a little piece of work. But I found that as I was at MIT, right, I was interested in a lot of things always, like super curious. And I was always interested in history of ideas. And I read Kuhn. I was quite influenced by Kuhn. But then I thought, this is not enough. This is how I was like a little kid. I was like, you know what? This is not enough. I think that he's missing something because he's not an active scientist.
Okay.
I mean, the person, if you sit outside, and I was like, this thing of being an insider and an outsider, because that was my life, right? My entire life, I've been a bit of an outsider and an insider at the same time. Growing up, etc., in my sort of history. So that was an idea that appealed to me. And I was like, you know what? I think one should roll with that. And that's what I want to be. So I also want to be a sort of philosopher of science and an active scientist. So, and I was young and I said, okay, I'm going to do this PhD and then I'll finish it and then I'll go back and do physics. And because I had sort of reached this impasse, I wasn't sure about what I wanted to do, right? Because I didn't want to do string theory. That was the automatic next step.
Right.
And so then I took this detour. And of course, I did not finish that PhD. My life went in a different direction. And the person who got me there was another, Brian, I don't know, do you think about this? I've had such good fortune. I'm so grateful to be able to do what I'm doing. I mean, I kind of reached it, I started out being very focused. Then there's a little bit of detours, but then I got to where I am in terms of always wanted to be a professor and a researcher and a scientist. And, I met, chance meetings, right? I met Martin Schwarzschild. He's one of my greatest heroes.
Yeah.
And he is no more. And he was, so what I was going to do in history and philosophy of science is in fields like cosmology, where you cannot perform controlled experiments and simulations are your experiment. How does that impact inference? How can you validate a theory and test it with a simulation? I mean, it's all related to the work that I'm coming.
The work you're actually doing now.
Right? So
yeah, these are questions, obviously, that are top of mind for folks who have gone into string theory, because oftentimes it's not even a simulation for us. It's just analytic mathematical equations and internal consistency as opposed to comparison with observations. So these issues are very close to many of us. But let me just ask you, I mean, do you feel like an outsider still?
In some ways, yes, right? I mean, I obviously intellectually I'm very much, in sort of an insider. But, as a woman of color, and as a person, there are many ways in which I feel that I stand out, and so also in the scientific style. That I work on my own, unlike most astrophysicists who are now, theorists are sort of joined into big collaborations of thousands of people as a pet theorist. I've not done that. And the reason I haven't done that is sort of a choice, because I want to take creative risks, and you can do that, in those sort of collaborations. It's a lot of consensus building about science and the scientific questions and how you tackle them. And I like to have this freedom of just running with an idea myself. So I work with smaller groups of people. So I think in that sense, I feel a little bit like an outsider. And, and Brian, you must too, right? Those of us who have interests that go well beyond, we don't fit the stereotype of what this kind of, intense scientist is supposed to be like. I mean, I know that we have a lot of things in common. We love to write. We like to engage with the written word as well as equations. And we think that science is a creative pursuit like many others. We're interested in art, in history, this, that. And so, I think there's an image of who is supposed to be a serious intellectual scientist. And I think there are people who probably would count me a little bit on the outside. And, I think people are not able to box me, I think. And when I was young, I found that really difficult because I so wanted to belong. I wanted to be one of the big boys, right? And then I actually realized now that, not being able to box you in any way, put you on the inside or the outside or whatever, is actually a very powerful position.
Yeah. Yeah, no, totally. I completely agree. I mean, there was a time when it was a lot of soul searching for me, and perhaps for you too. Should I spend my time solely doing research, when I'll write the most papers and have the greatest impact in science? Or should I split my time between doing the research and doing other things like writing books or doing TV shows or doing this kind of conversation that we're having here right now? And, the thought occurred to me that, you write a really good paper in physics and it influences a handful of 100 people typically, whereas you write a really good book or do a really good television show, you can influence millions of people. And so the influence is different and the impact is different, but there's value to each. And I've basically gotten to a point in my life, perhaps similar to yours, where I just do whatever feels right at a given moment, as opposed to try to fit myself within a particular rubric. The usual rubric, as you say, is you do your calculations, you do your research, you do it from the beginning, you become a graduate student until you leave the field, possibly in a box.
That's right.
And my view, there's just more to life than that. And so if you can flesh it out in interesting ways that have impact, all the better, all the more power to you.
I just find that my mind is stimulated. Like I find that, of course, you are incredibly powerful in your reach and how amazing clarity you have in explanation. I find that for myself, it's just that, when I am grappling with sort of ideas and histories of ideas and so on, it actually makes my scientific work much better.
Yeah,
absolutely. It pushes me. And, it is hard. I am trying to do like both with sort of equal intensity. It's difficult. And I think I can pull it off. I have to confess. I pull it off because I am a workaholic. Okay, whatever. I am a workaholic and I don't happen to have young kids or I have to care for or whatever, right? So I don't have those kinds of responsibilities that bind you, and it's all time. Everything is time.
Yeah.
But anyway, so I think, this kind of obsession with simulations. I met Martin Schwarzschild and he said, "What are you doing this for? Do you want to do simulations?" I said, no, I want to work with ideas. So then he said, "Oh, I know the person you need to go work with. I don't know why you're doing all this humanities, that you can always do that later, Priya, just learn how to write." I said, "Oh yeah, that was a hard thing to learn because I had to take all these graduate humanities courses." And then I went to Cambridge, England, and then my life changed. And then it was theoretical astrophysics, and it was, dark matter, black holes, and then idea was I would go back and finish. I'm ABD. I thought I'd go back and finish the PhD, but I realized that, as you said, that it's a better outlet to actually write a book and to express what I have been learning and digesting and thinking.
So you still do you have any thoughts of completing the other degree or?
Well, I do have a master's. I mean, I got a master's. I was there for 3.5 years. So and I actually quit. Actually, one of the frustrations, I was also frustrated with that, was because this was the time, again, dating us, when the sociologists of science were really kind of, it was the high point for them. So I was tired of having discussions with some of my brilliant classmates. Is this table made of atoms? Are atoms just a good way to represent whatever this table might be made of? And I'm like, no, guys. I've seen a diffraction pattern, and I think, yes, there is a conceptual model, but there's reality. And I was like, what? I am very open-minded about critiques of science and sociologists' critiques of science, and I think that scientists needed that. But I'm not for that extreme strong program. But that science, there's no content to science. Everything is context. I'm not there.
Yeah, me either.
I think it's not a sensible position. It's not supported. But anyway, that was the reason I wanted to quit. I was ready to leave as well and get back to science.
Got it. So I'd love to return. I want to return in a moment to your dark matter work. But before that, just since we've gone down this interesting trajectory, I mean, there may be young women watching this or will watch it on YouTube. Do you have any advice, for young women who are in a position that you may have been in 20 years ago, who want to be scientists? What words of advice would you give them?
Well, I don't have any great sagely words of advice. Luckily, things have changed a lot, and there's a lot more, many more opportunities to pursue science and different kinds of science now. I think, when I look back, I find that the thing, it's perseverance, persisting. It's a quality that we don't give as much credit to in terms of in science. But I mean, you will face a lot of obstacles. Everybody is going to, because I mean, there are going to be intellectual obstacles and other obstacles. Intellectual, because that's part of science, constantly trying to push your mind to learn more. So you have to love that frustration of pushing yourself more, right?
Yeah.
And I think you have to persist and not give up too easily, because you can give up intellectually, or you can give up because of circumstances, if you don't feel welcome somewhere. Or I think those other situations, the other circumstances are changing, and I wish they were changing faster. But I would say, it's just very glib to say follow your passion, but it is true. You have to kind of be stubborn, and you kind of have to stick with it. Wouldn't you say, Brian? I mean, it's advice to any young person.
Well, I mean, I give similar advice. I think the advice that you gave is particularly useful for you as a role model to other girls and women who would want to follow in this kind of trajectory. The more general advice that I typically give emerges from the fact that I have, and you probably have this too, I have a lot of young science students come to me and they want to immediately jump to the forefront. Like, I want to work on string theory, or I want to work on, I'm like, whoa, have you taken classical mechanics? Have you taken electromagnetic? Have you taken statistical mechanics? So I really emphasize to kids, like, watch programs like this and read books and see television programs, read New Scientist or Scientific American, whatever, to get excited about what's happening at the forefront. But you've got to focus in on the basics.
No, and get your foundations. Absolutely. I do the same thing. I have a lot of high school kids writing to me. I was like, I love black holes. Let me do research. Could you give me a project?
Yeah.
I'm like, you know what? Research is there for you. It's very exciting. As you say, follow it. But why don't you just master the foundations?
Yeah,
because that's what you really need. If you master the foundations, then, any research field you can get in, and you can make a contribution, and you can make an original contribution. I have no doubt, because I personally believe that, every kid, no matter what color, what gender, every kid has a very unique gift to bring to whatever they do. Be it science, be it the arts, be it any profession. The question, the big journey and adventure of life is to find what it is that is a good match to what you can creatively do. Your creative juices match the problem or the place where you can contribute. And all of us who are so fortunate to have made that connection early in our lives, but it's never too late.
Yeah, no, I agree. That is the big question. And I agree. I do feel incredibly fortunate in exactly the way that you described, that I sort of found something that fired me up, that I was good enough at to make a contribution in. And I mean, I sit here and I often, I'm in the middle of writing a book, like writing my last book, I said, I can't believe that I'm given the freedom to do this.
Okay. By the way, I loved your last book.
All right.
I love the ambition of it, because I really like the sort of ideas, grand synthesis of ideas.
Yeah.
I think it's very stimulating, and it takes time before you can write, right? So I'm holed up also writing a book, but I am getting distracted by my work.
Yeah, your wonderful last book, that was actually out just a couple years ago.
4 years ago.
4 years ago. Now time flies. Yeah. So you're in the middle of writing I'm
on this trail of understanding sort of radical scientific ideas. So that's the trail. I'm still on that same trail, kind of a new direction. But anyway, coming back. So, the obsession with simulations and the testing simulations was kind of always there for me. It was kind of a long thread. And so, I finished my PhD. I was very, very lucky, had a great advisor, did work really. It was a time of great personal turmoil. And I mention this only because, we always say that, great stuff happens when you're really troubled. Sadly, for me, that was true, that it was a moment of enormous personal difficulties in my life. And when I moved to England, and I poured myself into my work, and, you could tell that I gave it everything, and it became me. And it was kind of hard because I became a super workaholic at that point.
Yeah.
But then I was very fortunate. I barely did a postdoc. I became a fellow of Trinity College, and then I got the job at Yale. So once I came to Yale, I continued this thread of lensing, and lensing was new at that time. So the observational data was just coming in.
Yeah.
And the reason is you needed Hubble Space Telescope kind of resolution to start seeing it. And once you had it, you see lensing everywhere. I mean, and in clusters of galaxies, if you go and look an image of taken by Hubble Space Telescope,
beautiful.
You see, right? By eye, you can pick out all the distorted shapes. Even by eye, you can see it, right?
Just because the galaxies are normally, you know, elliptical or spiral, and they just have this sort of weird bend to them when you look at the imagery, because as we were saying before, the light is bent by the gravitational pull of the matter.
Yeah, and especially, so you have this cluster of galaxies. So, you know, I've honed in on the system of cluster of galaxies because they are the largest repositories of dark matter. So any lensing effect that you find would be most dramatic. And so, you know, you have all these distant galaxies. You have this cluster that is in between us and this whole population of galaxies in the universe. And you end up seeing very mangled images of the background. And the idea, so, you know, I was part of the process, you know, because I was early in on this game, developed the methodology to look at mangled shapes and infer back out instead, not just look at those and analyze them, but use that to figure out how much dark matter is in the lens.
Got it. Got it.
And the reason you can do that, you know, it sounds odd, like how could you really do that? Well, you know, galaxies are born with a distribution of native shapes. They have birth shapes. However, clusters are extremely rare in the universe. So they're very, I mean, you know, so when you look at the night sky, most often you are not looking through a cluster. They're very rare. So the rest of the night sky is not as distorted, which means you have the baseline. You know what the baseline is. And, you know, modulo that baseline, you're able to figure out. So in this work, we've just been following. So, you know, what you can do now is that as the data is getting better and better, you can compare with the theoretical conception of the cluster as this mountain ranges with peaks, go into a simulation, look at...
So let's look. So you showed it before, but people probably don't have it in mind. So you were able, literally from the observations of these mangled, distorted galaxies, you were able to, in essence, come up with a map of the distribution of dark matter in that region. And can we bring up, and the peaks and valleys that you're referring to is very dense dark matter here, less dense dark matter here, and so forth throughout the region. So if we can bring up a picture, is this an example of what you're referring to?
Yes. So this is from our work in 2017. So this is a cluster. This is the mass distribution in a cluster. And I just want to show that this purple stuff is actually a mound. It's above the baseline in the universe.
Okay.
So it's already heaped. And then on top of that heap, you have all these little peaks. And these peaks correspond to the location of cluster galaxies. So, you know, galaxy cluster has about 1,000-ish galaxies that are held together. And each of these peaks is associated with a cluster galaxy. You know, so that was the original conceptual model I told you, right? And that has stood its stead, and that is sort of verified as a useful way to conceptualize the distribution of dark matter in a cluster. And remember, we talked about, this is where the connection back to Vera Rubin and the individual galaxies come, right? So we saw that individual galaxies have their own extended dark matter. And when they fall into a cluster, some of the dark matter may be lost in the fall, but they retain their own clumps. So each one has its own blob and gloop of dark matter. And those are those peaks. So they're heaped. So dark matter is heaped in those peaks, as well as an overall kind of mound, which is a larger scale distribution.
And now you're able to compare this, if I understand, to the simulations that you're talking about and see whether the physics as we understand it, that's embodied in that simulation, is agreeing with the actual observations of the dark stuff through this indirect means.
Right. So you can go.
Is that your most recent paper? Is that what you do in that paper?
Yeah, that's exactly. And you know, we already, so what you can do, you can go into a simulation, you can look into a region where you have a cluster and count up these peaks. You can count up the peaks, you can look at their locations roughly, and And you what you do is you pick clusters in the simulation box in your universe that would produce the right amount of lensing. So they have the same amount of mass, and they are apt to give you, and you do this statistically, right? So you take as many clusters in a box, you can make many of them. So that was the original challenge over the years when I was trying to do it. These objects are rare. So your simulated box has to be quite large to have enough of them so that you can actually do a statistical analysis, right?
So you need a lot of computer power to have a box that large and stuff.
Yeah. And that became available, like the best kind of state-of-the-art simulation where you could do this became available in 2016. And that was the Illustris simulation. So this image, this dark matter map, it's the most detailed map still spatially of a cluster of the dark matter distribution. So what we did is we found that intriguingly, the number of clumps on average matched very well. But there was something amiss in terms of the detailed distribution of the clumps. So there was a hint that there was a bit of mismatch, a very small hint. And, and I really wanted to follow through. And that is where this new paper comes in. So one of the things that you need to pin down this model to get this, the heights of these peaks, are basically the amount of matter that is associated, dark matter, with an individual clustered galaxy.
Okay.
So then you have to play the Vera Rubin trick to go and measure the stars. So that these clusters are so far away that we have not measured like she did, the speeds all the way from the center to the outward, but we can make a central measurement, a key measurement of just the inner part, how fast are the stars moving. And that's what in this paper we were able to do with this wonderful spectrograph on VLT, the telescope operated by the Europeans. So we were able to get spectra, so detailed, accurate measurements, first to determine the membership without ambiguity that this cluster galaxy is actually sitting in the cluster. It's not in front of us, it's not behind us, right? So that's a crucial source of uncertainty in all the modeling. Before you can make any grand claims, you have to do like the basic sort of checking out. And then we made measurements of the speeds of stars in the centers of galaxies, and we made sure that they were incorporated into our mass model, which means we have the best observationally constrained at the moment distribution of dark matter. So then you can start doing some precision tests. And because the Hubble data is so deep, what you can do is instead of just looking at the large scale lensing, you can now zoom in and see if around any of these individual clumps, do any of these individual galaxies in turn double split the light themselves. So which means they produce smaller scale events. And you can see them in the insets, right, in this figure. So we found that because the data is so good now, right, so this is what is wonderful about the convergence. Like the data is good and the simulations are very sophisticated. So it's a good time to do a detailed comparison of the kind that we were doing. So what we found is that these small scale clumps with these individual peaks shown in the previous map, they are doing their own little lensing on top of the big lens. So it's almost like, because, this lensing, as you know, right, we have often make this analogy with just the usual glass optics lenses that we are all familiar with. It's almost like you have this one big smooth lens, and on top of that, you have a lot of little lenses.
Yeah.
And so what we did is we said, okay, let us look at a quantity. Let's devise a metric that can quantify the capacity of a cluster to do a lot of small scale lensing. And so we defined this metric. It's called galaxy strong lensing probability. And you can calculate that for real clusters in the universe. And we didn't do it just for one. It was a full sample of 11. And the data that we used, I told you with the speeds, the extremely well calibrated were 3 clusters. It's very expensive in terms of telescope time.
Yep.
But, in general, it kind of ratified our modeling and it showed. So we used 11. And then we calculated this quantity, which tells you the capacity of small scale clumps to do strong lensing, split images, not just mildly stretch them, but actually split them, like the cluster does.
Yep.
And like individual galaxies sitting in the field also do. So that is known, that it does happen. Individual galaxies can have enough mass to do the splitting themselves. So we were very surprised that we found such events in the clusters. But then we went into, and with this metric, we calculated the probability, and we did the same calculation in the simulations, and we found a mismatch of an order of magnitude.
I see.
And that is huge because, and then
big mismatch. Yeah.
Yeah. And so, simulations do not have cluster galaxies concentrated enough to have the capacity to produce as many of these strong lensing events on small scales.
So what does that tell us?
Well, we could be missing an ingredient in the simulations of clusters. Clusters are really complicated. They're very dynamical. And, there are...
Could it be as simple as, like, you don't think it's like a bug in the code or anything as simple as that, because the agreement with the other qualities is just too close for...
That's right. And we tested it with 3 different sets of simulations done by different groups with, different methods and, different approaches even computationally.
I mean, just to give us a sense, these simulations, like, can you describe in terms of lines of code? I mean, how big are the computer programs necessary to...
They're just huge. I mean, and they're modular. So I mean, some of them could be close to several 100,000 lines of code.
Wow.
because these contain recipes for the formation of galaxies, for black hole activity. What does the black hole do? And some of these things we kind of have to put in by hand. It's well motivated, but we put in by hand. So if you add in all the pieces of physics that have to be put in, it's a lot of code.
And like, how much general relativity is in this code? Is it mocked up in a Newtonian way, or is it like full general relativity?
Well, it is patched, right? So the scales on which general relativity is relevant and important, it is part, so the expanding universe background is very much they are quite realistic. And then, of course, in the regions of the universe that have decoupled from the rest of the universe, like an actual galaxy, there it's all Newtonian pretty much, right? So I think they patch in, they're self-consistent. These are amazing bits of code, and it's an incredible achievement to have kind of codes that we have. And we have a multiplicity of them now. And they, there's all these adaptive meshes where you can refine and zoom in without losing the larger scale. You don't make the kind of trade-offs. I mean, still, of course, the number of particles is finite and you could do better and so on. But it's pretty spectacular with the billions of particles, right?
Yep.
So what we found was that this mismatch means that maybe there's a physical process that is missing in the simulations.
When you say missing in the simulation, you mean that perhaps we've just been missing, right? I mean, this could be pointing to something that we're just unaware of, and that's why it's not in the simulation.
Right. A physical process that we have assumed is not important or doesn't occur, or we haven't even understood, as you say, occurs in clusters.
Right. Now, what about for dark matter, though? Is this a potential challenge to the whole dark matter paradigm?
Right. So the other possibility is that there's something fundamental about the nature of dark matter we have missed. So we have, with this cold dark matter model,
by the way, quickly tell us why cold. I don't think we ever talked about the cold.
We did. So it's because these particles move extremely sluggishly compared to the speed of light. So it's cold.
Good. So go on from there. Sorry, just wanted to talk about that.
Not at all. And so these, we have attributed only gravity to them, which means they condense and aggregate only via gravity. There's no other force, there's no other interaction that can squeeze them further. And so, they have a peculiar equation of state, right? Sort of in chemistry, we know from gases, like we know what the equation of state, like Boyle's law. So the pressure, the volume, and the temperature are related. So if you squeeze gas with a piston, you increase the pressure and so on. But cold dark matter is really peculiar because the equation of state is P equals 0. It's pressureless, which means it doesn't collide with itself because, pressure you have only because molecules collide with themselves or with a container or whatever. But since these particles are collisionless, they don't collide with each other. You can't condense them. You can't, you don't lose energy and dissipate and become more compact. You can't concentrate dark matter to the levels that you can concentrate ordinary atoms, which is why the centers of galaxies are so replete with stars, right? They are very high density of stars because gas can collapse and it gets denser and denser because it has pressure and the density goes up. And I think you mentioned in one of the questions I was listening in earlier, somebody was asking you about star formation. So because there's pressure and you can squeeze the density and you eventually ignite nuclear fusion, you can't do that for dark matter because you just can't squeeze it in enough. There's no force that permits you to squeeze it in. So it's just gravity, and it's kind of this loose aggregation.
Yep.
So this suggests that in the centers of cluster galaxies, somehow the matter distribution is much more concentrated. So you have ordinary matter, of course, there, and you have dark matter, right? And so it obviously we could be missing. Maybe there is, I'm not going to speculate too wildly, right? But it could be that dark matter either interacts with itself and squeezes somehow itself to get more concentrated, or it interacts with ordinary atoms or baryons in a way that allows it to dissipate and squeeze and get more concentrated, basically. And, and I think what is intriguing, though, about both of these options is that they're both really significant implications for the field and our thinking about dark matter. If you're missing, simulations have been the backbone of this field, because we can't do controlled experiments, remember? So that's our experimental lab. And if you're missing something there, I think it behooves us to pay attention to figure out what it is, right?
Hugely so. I mean, have there been any theoretical papers, perhaps written before or written since, probably too soon, although people work very quickly, that offer a theoretical answer that meets the mismatch between the two?
No, I mean, I haven't, and there's been nothing. So first of all, we kept our results under wraps like we are supposed to. And so we didn't really leak it to anyone. So our colleagues are just learning about it.
Yeah.
The hint that I found in 2017 paper, that's out there. That's been out there. And I think people have been looking at possibilities. There's some suggestions. And in this paper in Science, right, you have all the supplementary material. There's 14 pages of validity tests in which we actually kind of look at all the possibilities, many of the obvious possibilities. Maybe the simulation isn't good enough. Maybe you missed something. Maybe the black hole activity is moving out too much matter from the centers. Because that's what we want the black holes to do, to explain other things that we see. So, we ran simulations in which we turned off black hole activity completely. Yes, we can get rid of a little bit of the discrepancy. But, the thing is, it's a knowing gap. It's like, an order of magnitude is quite large. Factors of 2 we can see. And there aren't factors of 5 different factors of 2 that would all combine in the right way. I mean, we just couldn't find anything, which is why the paper is open-ended.
Well, that's great.
Yeah, the other question about the nature of dark matter is, problems on small scales with the cold dark matter. And people have suggested solutions. But, those problems go in the opposite direction. You need galaxies, the centers of galaxies, to be not so concentrated. You need them to be smoothed out. But those were problems that were detected not in a cluster environment, but for individual galaxies. Galaxies like the Milky Way, not sitting in the middle of this kind of, happening cluster.
Yeah. Well, look, although it may be a myth with Newton and the plague, we like the story. Maybe this really will upend the dark matter paradigm in some significant way. And you will have used your time away from ordinary world in a very productive way, if indeed that's the impact of this work. Right. So it's a beautiful paper.
Thank you so much.
I think it's going to have a lot of impact. I think a lot of theorists are going to try to rise to the challenge and come up with ideas that bridge the gap between the simulations and the observations. And I think it's going to be a very exciting time. So
thanks
so much for spending some time going over, all sorts of ideas. I want to quickly mention for the audience that Priya has a World Science U course that is going to be released, I think, in the next week or 2 or 3, something of that sort. I don't have the exact date in front of me, but you guys should keep your eyes out from that. It's, again, a wonderful exploration of these kinds of ideas. And we look forward to whatever forthcoming book emerges from your, radical studies about how science is done. And it's been a pleasure speaking with you. So, and I
Thank
hope
you so
that
much.
we can speak again sometime.
Yeah, I miss coming to the World Science Festival. I come even if I'm not speaking. It's a train ride away for me,
Yeah.
so I really miss all the activities. Hopefully, we can all do stuff in person before long.
Yeah, I appreciate that. And again, the festival's not going to stop. We put it on hiatus to figure out the best way to do it digitally, as I mentioned earlier in the conversation to the YouTube audience. And so, no doubt, we'll have you in some World Science Festival programs going forward, whether it's live or digital. But for the moment, of course, it will be digital. But yes, I certainly look forward to our paths crossing in a literal as opposed to a virtual sense.
Right. And yeah, I want to say thank you to you for all that you do, Brian. It's
Great.
very important work.
Thank you very much. And thanks for
Very
joining.
inspirational. Yeah.
Appreciate that. Thank you. All right. So thank you very much. And we're going to just do a little bit more Q&A before we wrap up. I'm not going to go quite as long as I sometimes do for reasons that I will not articulate explicitly, but just to say that I have to get back in shape for sitting still for 3 hours when one is drinking a lot of water. Okay. A couple of questions before we wrap up here, which is a great conversation. I hope you guys enjoyed that discussion of dark matter and the various ways in which scientists try to analyze its presence indirectly. Dark, you don't see it, but you analyze its presence through its effect on the things that you can see. And through the way that it lenses, as Priya was describing, you can map it out, and then you can compare that to the way the dark matter should be distributed based on your understanding of what it might be and the ways in which it interacts. And that mismatch is a powerful clue, perhaps to either what dark matter is or to the fundamental laws of the processes that it engages in. Okay, so what else do we have here? I'm able to do a question too before we wrap up here. So Jim Blond says dark matter will go the way of the ether, and it may well be the case that just as in an earlier generation, the notion of an ether was hypothesized to make sense of observations having to do with light. We have hypothesized some more invisible stuff to make sense of our observations today of motions of galaxies and motions of stars and galaxies. And you're right. That may be a stopgap measure which goes away with a deeper understanding of the laws of physics. So I'm not in any way saying that that isn't how things will turn out. We just do not know at the moment. Alex asks, Odegu asks, Brian, what would be a bigger discovery, life on Venus or dark matter? I'm not one for creating hierarchies that much in discoveries. I don't really... People often say, who's the better scientist? Was it Newton or was it Einstein? I'm like, at that level, it's so spectacularly high that it doesn't matter. The hierarchy doesn't matter. But, in some sense, the discovery of dark matter would confirm something that we've long suspected to be true. So I think many people, if dark matter turns out to be a weakly interacting massive particle, a WIMP, as Priya described it, if that turns out to be the case, I think everybody would be, wow, that's spectacular. But in the end, we'd nod our head at having confirmed something that we thought would be the case. Life on Venus is not something that people have really spent a lot of time developing and thinking about. So its immediate impact on the scientific community might be larger. But again, the point is any of those discoveries would just be spectacular, off scale, once in a generation kind of insight. So it's just exciting across the board without any need to order the various discoveries. Alfred asks, could you do a narration from the Big Bang to quantum physics? A narration, like a sort of a show. And yeah, I should say, I mentioned my book before, Until the End of Time. Again, library, I'm not selling it, but I mention it in response to Alfred's question because we're also in the early stages of developing a television adaptation of that, and that would go from the Big Bang to quantum physics and beyond. So there may be something of that sort in the not too distant future. All right, final question before I have to leave. Rajev asks, why is light massless? And light didn't have to be massless. Our understanding of its dynamics, of its physics, how it behaves, points in the direction of it being massless, and our observations of it, which are quite precise by this point in the game, suggest strongly that it is massless. But, you know, if it turned out that way down in the future with ever greater precision, somehow we're able to measure light and its property, it has a little tiny mass so small that today's detectors would be unable to be sensitive to it, we would find a way to accommodate it. And it would change fundamentally our understanding of the basic equations and the basic properties of light as a transmitter of the electromagnetic force, but we would be able to accommodate it. So it's just to say that light doesn't have to be massless in the sense that it would be logically inconsistent to ever imagine light as a massive particle. I mean, the transmitter of the weak interactions, the W and Z bosons, these are massive particles. And they are transmitting a force much the same way that the photon does. So it doesn't have to be logically speaking massless, but everything that we know points to it being massless. All right, with that, I'm gonna wrap it up for today. Again, thanks for joining us for our first Q&A hour, and then this discussion in the second hour with Priya on dark matter. And we will announce, I'm not exactly sure if we're going to stick at this time going forward, but we're always open to hearing suggestions for a more convenient time, and we try to take that into account in scheduling these events. If you want to make suggestions for who you'd like perhaps to join in for part of these discussions, happy to hear those suggestions as well. And with that said, keep a lookout for Priya's World Science U course. Take a look at my own World Science U course on special relativity. That's sort of a 12-hour version, and there's the 2-hour version that are out there in the world, Space-Time and Einstein. And so until we meet again, take care. I've enjoyed the time we spent today together. Bye.